Today we'll be going over Unit 1.5, which is over atomic structure and electron configuration. So all of this kind of begins with the shell model of an atom. So there are forces of attraction between electrons and the nucleus because they are oppositely charged. So opposite charges attract one another while opposites repel one another. So remember, the nucleus has positive protons and then neutral neutrons. So as a whole, the nucleus is positive. Electrons carry a negative charge, so that is why the electrons are attracted to the nucleus. They exert positive attraction forces on one another. Coulomb's law is something that will show up again and again, and it basically describes a force of attraction and how strong that force of attraction is. So K is just a constant, and then the value Q is the magnitude of charge of a particle. So in most cases we're talking about protons and electrons. D is the distance between charged particles. Sometimes D can be replaced with R, which is the radius of the atom. But this Coulomb's law can be used to make predictions about the forces of attractions between electrons and the nucleus. So if we increase the number of protons, we are increasing the magnitude of the charge of a particle because we're increasing the number of protons. So that makes that force of attraction stronger. But if we increase the distance between the particles, so the nucleus and the electrons, the force would be less, it'd be weaker. So the shell model of an atom states that electrons move in the nucleus in a circular orbit, and only certain orbits are allowed. So this means it's a quantized value, which means it can't be in between shells 1 and 2. It can only be in shell 1 or in shell 2. So Bohr is the guy who came up with this model, and he labeled the orbits n equals 1, n equals 2, etc., and called the integers quantum numbers because each one is associated with a quantized energy level, which means, again, electrons can't be located between energy levels. They're either at one or another. According to Coulomb's law, the forces of attraction between electrons in the nucleus in n equals 2 are less than the forces of attraction between electrons in the nucleus in n equals 1. The reason for that is that the distance is greater. So relative charges are the same, but since distance increases, the force of attraction is less. We also have inner core and outer core or valence electrons. So inner electrons are contained in inner shells and valence electrons are in the outermost shell. Elements can have up to 8 valence electrons, and valence electrons are always in the s and p subshells of the outer shell. So the orbital model here doesn't really show what s and p mean, but we'll get into that a little bit later. And we'll discuss some a little bit later, but the valence electrons are in s and p subshells. They're not going to be located in like the d and f subshells. But you'll notice here sodium has 1 valence electron, while argon has all 8. So typically elements like to be like the noble gases, which have a full valence shell of electrons. So electrons really describe how an element is going to react with something else and determines their reactivity. With inner and outer core electrons, or valence electrons, we have what's called the shielding effect. So electrons that are furthest from the nucleus are partly shielded by inner core electrons. So I always kind of compare an intro chem to like being at a concert. If you're in the back row of the concert, you're kind of shielded from the stage by the crowd in front of you. In reality, the shielding isn't because like electrons can't see through. It's actually because electrons are repelled by one another. So since between the outermost valence electrons and the nucleus are a bunch of other negatively charged particles, the outer core valence electrons are shielded. So they don't like the other negative charges because like charges repel one another. So that's where the shielding actually comes from, the electrostatic repulsion from inner core electrons. What else? So We talked about Coulomb's law, how outer shell electrons, the force of attraction is less because of distance. It's also less because of the shielding effect. So what we would predict it being based just on Coulomb's law, it's actually less than that because of the shielding effect as well. Next topic we want to talk about is first ionization energy. Sometimes you'll hear it called ionization potential instead of ionization energy. Those two things are the same thing. Different words for the same thing. But ionization energy is the minimum amount of energy that is required to remove an outermost, least tightly held electron from an atom in a gas phase. So for ionization energy to be found, the element must be in a gaseous phase. It's the energy that it takes to remove one electron, the outermost, easily, least tightly held electron. Energy always has to be added to the system in order for ionization to occur. So in order to strip away that electron, you have to input energy, which means that this is always an endothermic process. And the value for energy is going to be a positive value. If the value of energy was negative, that means that energy would be released as we ionize the gaseous element. Values are obtained by shining different frequencies of light on a pure sample of neutral atoms that are in the gaseous phase, and then they record the frequency that removes an electron using the equation, and we'll get into this equation later on, but energy equals HV, which is basically energy is directly related to the frequency. And they use that frequency that they use to strip the electron to calculate energy. You will learn about this relationship later in the course, so you don't really need to understand it now, but just know that the energy is related to the frequency of light that they shined upon the gaseous element to strip that electron. Okay, so there's your definition. Minimum amount of energy that's required to remove an outermost, least tightly held electron from an atom in the gas phase. So yes, it does have to be in the gas phase. We can make elements into the gaseous phase easily to record ionization energy. So even if it's not naturally a gas at room temperature, we can always make it into a gas. So if we plot first ionization energy, we can see a clear trend, and right now it doesn't look like much. But this data kind of shows two things. One, ionization energy decreases when moving down a group in the periodic table. Okay, so remember your groups are the columns. And ionization energy generally increases when moving left to right across a period in the periodic table. So periods are your horizontal rows in the periodic table. So you can see from going hydrogen to helium, it's an increase in energy that is moving from left to right across the periodic table. Going hydrogen, lithium, sodium, potassium, that's going down a group or family in the periodic table. So this slide kind of shows that trend in ionization energy, and there are plenty of periodic trends out there that we will get into in Unit 1.7, but ionization energy is just going to be the first trend that we kind of talk about. So you'll learn more about why in 1.7, but this is the general trend you will see in ionization energy. So if we look at hydrogen and helium, the ionization energy of hydrogen is 1,312 kilojoules per mole. So that's how many kilojoules it takes for the ionization energy of 1 mole, versus helium is 2,372 kilojoules per mole. So helium is almost twice the ionization energy of hydrogen, and this can be explained because of Coulomb's law, because helium has twice as many protons as hydrogen. So Q is increasing. The electrons that are in hydrogen and helium are relatively the same distance from one another because they both only have a 1s shell. So since distance isn't changing while Q is changing, it's increasing, we expect that force of attraction to be larger. If there's a larger force of attraction, to strip away those electrons, it's going to take an input of more energy. Okay? So if you kind of think about kids and candy versus vegetables. Kids aren't really attracted to vegetables very much. So you can easily take some from their plate without them throwing a fit or anything. But candy, if you try to take their candy, they're going to throw a huge fit because the attraction is so much higher. So it takes more energy and effort to kind of take away that candy. Now if we look at lithium, so that should be hydrogen and lithium, sorry, ignore that typo. Lithium is less than half as large as the ionization energy of hydrogen. So if the most loosely held electron in lithium was the same distance from the nucleus as those in hydrogen and helium, then you would expect the ionization energy to be greater than that of helium, okay? Because the distance is the same, and we would be increasing Q according to Coulomb's law. But since the most loosely held valence electron in lithium is not the same distance, it must be further away because it is easier, it takes less energy to strip that electron away than it is for hydrogen. So distance is increased, which would make the force of attraction less, making it easier to take away that valence electron from lithium. So ionization data suggests that electrons are arranged in shells, okay? So that lithium doesn't just have one shell with 3 electrons, it has an additional outer shell with its valence electron. So in this model, electrons move in a 3D shell, so we kind of depict it as a 2D dimension, but they are 3D. Each shell has an exact set distance from the nucleus, so the electron that remain in a given shell of a neutral atom are always the same distance from the nucleus. So it requires much less energy to remove the most loosely held electron in lithium because the distance is greater, and the N1 shell we know can only hold up to 2 electrons. Moving from left to right across the second period, 8 electrons can be added to the n equals 2 shell. So n equals 2 can hold up to 8. So before, n equals 1 could only hold up to 2. Using the periodic table trends, n2, the second shell, can hold up to 8. If we go down to the third period, we find that the third shell, n equals 3, can hold up to 18 electrons. So it can hold at least 8, but we know that it can hold up to 18 electrons, and this will be discussed with the electron configuration in the second half of this lesson. So the first row of the periodic table has 2 elements. This is just kind of a summary. So n equals 1 can hold 2 electrons. Second row has 8 elements and could hold 8 electrons. Third row has 8 elements and can hold at least 8 electrons, but it can actually hold 18, which we will see when we talk about electron configuration. So we talked about the shell model, which is okay, but has some limitations. The quantum mechanical model is the best model that we have of the atom. So in this model, computers are used to determine the approximate size and shape of orbitals for different elements. So it requires a lot of calculations. It uses the wave function formula to work on multi-electron atoms, unlike Bohr's formula. And it accounts for the different energy levels or subshells within a shell. So before we're talking about just shells, now we're talking about orbitals and subshells. Every electron within a given subshell of an atom, which is 1s, 2s, 2p, is at the same quantized energy level. So electrons do not follow perfect orbits like the shell model kind of predicts. Wave function describes an electron's possible position in a 3-dimensional space, which is now what we kind of call an orbital instead of a shell. And the different possible wave functions are 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, etc., up until 7f orbitals. Every electron under one of these labels in a given atom is at the same quantized energy level. Okay, so the number in front of it describes its quantized energy level. And that's it for this first video. We'll get into more about what an orbital is starting in the next video.